The new observations of the James Webb Space Telescope have brought Cassiopeia A back into the spotlight. These discoveries not only help us better understand the processes behind supernova explosions, but also provide new insights into the nature of the universe. Looking at the history of Cassiopeia A, we better understand why this remnant is so important in the world of astronomy. A supernova explosion marks the dramatic end of a star's life cycle and is a major source of the chemical richness of our universe. This remnant serves as an excellent laboratory for studying these processes. This supernova remnant is located approximately 11,000 light-years away in the constellation Cassiopeia. The supernova explosion that occurred in 1680 was not observed with the naked eye from Earth. However, this remnant was discovered through radio astronomy in the mid-20th century and has been the subject of many studies since then. So what did the Webb telescope find in this remnant? What new discoveries were made, and how do they contribute to supernova research? In the continuation of this series, we will explore the new face of Cassiopeia A to answer these questions. Let's embark on this incredible journey together and try to unravel the mysteries of the universe. Cassiopeia A, like other supernovas, represents rare yet extremely fascinating events in the universe. A supernova explosion occurs in the final stage of a star's life cycle. As the star exhausts its fuel, immense pressure builds up in its core, causing the star to collapse in on itself and then explode in a massive burst. This process releases an extraordinary amount of energy and creates new elements. The evolution of this supernova remnant began with an explosion that happened approximately 340 years ago. However, how the remnant evolved after the explosion can be understood more clearly thanks to powerful telescopes. The Webb telescope helps us better understand this evolution by closely observing the internal structure of the remnant and the gas and dust clouds left after the explosion. Why are supernova explosions so important? They are fundamental processes that enrich the universe with chemicals and elements. For instance, heavy elements like iron in our bodies are formed during supernova explosions and are scattered into space. Therefore, supernova remnants like Cassiopeia A represent not just the death of a star, but also the birth of new elements. The telescope's observations allow us to examine the post-explosion evolution of the remnant in more detail. These observations help us understand how the gas and dust clouds left after the explosion have formed and changed over time. This helps us better understand the evolutionary processes of supernova explosions. The Webb telescope is one of the most powerful and sensitive space telescopes ever built. Its advanced technology allows us to see even the smallest details in the depths of the universe. Supernova remnants like Cassiopeia A can be studied in more detail than ever before thanks to its high-resolution imaging capabilities. This advanced telescope uses various instruments to observe this remnant. These include NIRCam, near-infrared camera, and MIRI, mid-infrared instrument. NIRCam enables detailed observation of the internal structure of the supernova remnant and the gas and dust clouds formed after the explosion by imaging in infrared wavelengths. MIRI, on the other hand, works in mid-infrared wavelengths, analyzing the chemical composition and temperature distribution of these structures. The telescope's observations of Cassiopeia A have revealed many new insights. For example, we have discovered details of the gas and dust clouds left after the explosion that we had never seen before. We have found answers to questions such as how these clouds formed, what elements they contain, and how they evolved over time. Its high-resolution images help us understand the internal structure of Cassiopeia A and how this structure has changed over time. These observations enhance our understanding of the evolutionary processes of supernova remnants. For example, we have learned how the dense gas and dust structures left after the explosion interacted with the surrounding environment, and how these interactions triggered the formation of new stars. These observations not only provide more information about the evolution of Cassiopeia A, but also offer a broader perspective on the general mechanisms and consequences of supernova explosions. Now, Let's move on to the next section, where we will examine the gas and dust structures formed after the explosion in this supernova remnant. We will discuss how the telescope identified these structures and what the findings mean. The structures formed after the explosion in Cassiopeia A are among the most striking features of supernova remnants. The immense energy released during the explosion ejects the outer layers of the star into space, leaving behind dense gas and dust clouds. These structures provide important clues about the intensity and nature of the explosion. Thanks to the telescope's superior observational capabilities, these gas and dust structures can be studied in unprecedented detail. Instruments like enriched and MIRI analyze the internal structure, chemical composition, and temperature distribution of these structures. These analyses help us understand how the material left after the explosion has shaped and evolved over time. The observations have revealed that the gas and dust clouds in Cassiopeia A are complex and dynamic. For instance, dense clumps of matter, shock waves, and turbulent flows were detected within these clouds. These structures show how the energy left behind by the explosion has played a role in shaping the remnants. Additionally, the observations have uncovered the distribution of heavy elements in this remnant. These elements are formed during the explosion and are ejected from different layers of the star into space. Such observations help us understand how supernova explosions contribute to the chemical diversity of the universe and play a role in the formation of new stars and planets. The detailed data provided by the telescope allows us to better understand the post-explosion evolution of Cassiopeia A. These findings offer important insights not only for this supernova remnant, but also for supernova explosions and remnants in general. Now, let's move on to the next section, where we will examine the role of supernova explosions in the formation of heavy elements and how the elements in Cassiopeia A were verified by observations. A supernova explosion is one of the key sites for the formation of heavy elements in the universe. The intense pressure and temperature in the star's core lead to the formation of heavy elements like iron. However, even heavier elements are formed under the extreme conditions of a supernova explosion. Supernova remnants like Cassiopeia A carry traces of these elements, showing us how the chemical richness of the universe was formed. Observations of this remnant reveal the distribution and structure of these heavy elements in detail. Instruments like MIRI, mid-infrared instrument, and NIRCam, near-infrared camera, conduct spectral analyses of the different elements within this supernova remnant, identifying which elements are present and their concentrations. For example, the observations have revealed large amounts of oxygen, silicon, and iron in Cassiopeia A. These elements are formed during the explosion and ejected from the star's core into space. Post-explosion shock waves shape the distribution and structure of these elements. The distribution of these elements in Cassiopeia A provides important clues about the intensity and nature of the supernova explosion. For instance, regions with dense iron may indicate the high pressure and temperature conditions in the core during the explosion. Similarly, the distribution of oxygen and silicon shows how shock waves formed after the explosion have propagated and played a role in shaping the remnant. The data help us better understand how supernova explosions contribute to the chemical diversity of the universe and the formation of new stars and planets. These findings shed light on the chemical evolution processes of supernova remnants, helping us more comprehensively understand the formation and evolution of the universe. Now let's move on to the next section, where we will examine the evolution of supernova remnants and their contributions to the galaxy. We will explore how this remnant has changed over time and how it has contributed to the surrounding galaxy. Supernova remnants undergo significant evolution in the post-explosion processes. The immense energy released during the explosion ejects the outer layers of the star into space, leaving behind dense gas and dust clouds. These clouds cool and condense over time, triggering the formation of new stars and planets. This supernova remnant is a perfect example of these evolutionary processes. The high-resolution images provided by the telescope help us understand how this remnant has changed and evolved over time. For instance, The shock waves formed after the explosion play a crucial role in shaping the gas and dust clouds in the remnant. These shock waves cause the condensation of matter and the formation of new structures. The contributions of Cassiopeia A to the surrounding galaxy are also significant. Supernova explosions enrich the surrounding environment and stimulate the formation of new stars. The heavy elements ejected into space during the explosion serve as fundamental building blocks for new stars and planets. This process increases the chemical diversity of the galaxy and creates the necessary conditions for the formation of life in the universe. The observations help us better understand how this supernova remnant has contributed to the surrounding galaxy. For instance, the interaction of the remnant with the surrounding gas and dust clouds after the explosion triggers the formation of new stars. This process shows that the galaxy is in a constant state of transformation and renewal. The evolution of this supernova remnant provides an important example of the impact of supernova explosions on galaxies. The changes in this remnant over time and its contributions to the surrounding galaxy show that the universe is in a constant state of transformation and renewal. The data help us better understand these processes and more comprehensively study the evolution of the universe. Now let's move on to the next section, where we will examine the energy release of supernova explosions and its impact on the remnants. We will explore how the telescope analyzed the energy distribution in this supernova remnant and the role of this energy in shaping the remnants. A supernova explosion is one of the most powerful and energetic events in the universe. This explosion is characterized by the sudden collapse of the star's core, followed by the release of massive energy. Supernova remnants like Cassiopeia A allow us to study how this energy is distributed after the explosion and its impact on the remnants. The telescope is an ideal tool for analyzing the energy distribution in Cassiopeia A. Various instruments measure the energy density and temperature distribution in different regions of the remnant, revealing how the energy is distributed after the explosion and how it shapes the remnants. The energy distribution in Cassiopeia A provides important clues about the intensity and nature of the explosion. For example, observations detected intense energy release and high temperatures in regions close to the center of the remnant. This indicates the high pressure and temperature conditions in the core during the explosion. Additionally, the outer regions of the remnant have lower energy density and cooler gas and dust clouds. This energy distribution helps us understand the impact of shock waves formed after the explosion on the remnants. Shock waves compress gas and dust clouds under the influence of the energy released during the explosion, and this compression can trigger the formation of new stars and planets. The data show how these shock waves propagate in the remnant and the role they play in shaping the remnants. Analysis of the energy distribution in Cassiopeia A helps us better understand how supernova explosions contribute to the chemical diversity of the universe and stimulate the formation of new structures. These findings show that supernova explosions not only mark the end of a star, but also signify a continuous transformation and renewal in the universe. Now, let's move on to the next section, where we will examine the new discoveries made in Cassiopeia A and how these discoveries contribute to supernova research. We will explore the findings from new observations and their potential impact on future research. The high-resolution images and spectral analyses provided by the telescope have revealed many new insights about Cassiopeia A. These new discoveries help us better understand the evolution and structure of supernova remnants left after explosions. First, the data have uncovered details about the gas and dust clouds in this supernova remnant that we had never seen before. The dense clumps of matter and shock waves present in this remnant offer important information about the complex structures formed after the explosion. For example, observations show dense gas and dust accumulations in the center of the remnant and how these structures have evolved over time. Additionally, spectral analyses have detailed the distribution and chemical composition of elements in Cassiopeia A. These analyses show how heavy elements formed during the supernova explosion are distributed within the remnant and how they change over time. These findings help us understand how supernova explosions contribute to the chemical diversity of the universe and influence the formation of new stars and planets. Observations of Cassiopeia A also help us better understand the impact of shock waves formed after the explosion on the remnants. These shock waves compress gas and dust clouds, stimulating the formation of new structures. The data show how these shock waves shape the remnants and contribute to the surrounding galaxy. These new discoveries help us better understand the chemical and structural diversity in the universe caused by supernova explosions. The detailed data allow us to gain more insights into the evolution of Cassiopeia A and make significant contributions to supernova research in general. Now, let's move on to the next section, where we will examine the challenges of observing supernova remnants and how these challenges were overcome. We will explore the high-resolution images obtained from Cassiopeia A and how these images contribute to supernova research. Observing supernova remnants is a challenging task for astronomers. These remnants are often surrounded by dense gas and dust clouds, making it difficult to obtain detailed images. Additionally, analyzing the internal structure and chemical composition of these remnants requires high-resolution imaging and precise spectral analyses. The James Webb Space Telescope is equipped with advanced technology and instruments to overcome these challenges. Instruments like NIRCam, near-infrared camera, and MIRI, mid-infrared instrument, are ideal for analyzing the internal structure and chemical composition of supernova remnants in detail. These instruments image in infrared wavelengths, revealing the details within gas and dust clouds. The high-resolution images allow us to see the internal structure of this supernova remnant and the gas and dust clouds formed after the explosion more clearly than ever before. These images enable us to examine the dense clumps of matter, shock waves, and turbulent flows within the remnant in detail. Additionally, these images help us understand how the remnants left after supernova explosions evolve and change over time. The telescope's observations also allow us to analyze the chemical composition and element distribution of supernova remnants in detail. These analyses show how heavy elements formed during the explosion are distributed within the remnants and how they change over time. These data help us understand how supernova explosions contribute to the chemical diversity of the universe and play a role in the formation of new stars and planets. These high-resolution images and detailed analyses help us better understand the evolutionary processes of supernova remnants and their contributions to the surrounding galaxy. The data allow us to gain more insights into the evolution of this supernova remnant and make significant contributions to supernova research in general. Now, let's move on to the next section, where we will discuss the cosmic significance of supernova explosions and what this remnant represents in this context. We will explore the role of supernova explosions in the universe and how the telescope has contributed to understanding these explosions. Supernova explosions are among the most dramatic examples of the cycle of birth, death, and rebirth in the universe. These explosions, occurring in the final stages of a star's life cycle, not only mark the end of the star, but also scatter elements into space that trigger the formation of new stars and planets. This process signifies a continuous transformation and renewal in the universe. Cassiopeia A is a vivid example of this cosmic cycle. The supernova explosion that occurred approximately 340 years ago ejected the outer layers of the star into space, enriching the surrounding environment. The data allow us to study the internal structure of this remnant and its post-explosion evolution in detail. Such supernova explosions play a critical role in the formation of heavy elements in the universe. Elements like iron, gold, and uranium are formed during supernova explosions and are scattered into space. These elements serve as fundamental building blocks for new stars and planets. Therefore, supernova explosions are important events that increase the chemical richness and diversity of the universe. The cosmic significance of Cassiopeia A represents not just the end of a star, but also the beginning of new life cycles. The detailed study of this remnant helps us better understand the role and importance of supernova explosions in the universe. The high-resolution images and spectral analyses reveal the internal structure, chemical composition, and evolutionary processes of Cassiopeia A in detail. These findings help us better understand the cosmic significance and role of supernova explosions in the universe. Examples like this supernova remnant show that the universe is in a constant state of transformation and renewal. The data allow us to study this process in detail and gain a more comprehensive understanding of the evolution of the universe. Finally, let's move on to our concluding section, where we will discuss the general contributions of the new face of Cassiopeia A discovered by the telescope to supernova research and how these findings can be used in future research. We will evaluate the overall contributions of the data to supernova research and their potential impact on future studies. Cassiopeia A, thanks to the high-resolution images and spectral analyses provided by the telescope, allows us to study the evolution and structure of supernova remnants left after explosions in unprecedented detail. These observations help us understand how supernova explosions contribute to the chemical diversity of the universe and play a role in the formation of new stars and planets. Discoveries in this supernova remnant have made significant contributions to supernova research. These discoveries have helped us better understand the mechanisms of supernova explosions and the evolutionary processes of the remnants they leave behind. In particular, the chemical composition and distribution of gas and dust clouds formed after the explosion show how such explosions increase the chemical richness of the universe. These findings have great potential for future supernova research. The data serve as an important resource for studying the evolution of supernova remnants and their contributions to the surrounding galaxy. These data can be used in the study of other supernova remnants and offer a broader understanding of the general mechanisms of supernova explosions. Future research can use the data to study the evolutionary processes and chemical compositions of supernova remnants in more detail. These studies can help us better understand the role and importance of supernova explosions in the universe. Additionally, they can contribute to the development of new technologies and methods to overcome the challenges of observing supernova remnants. The new face of Cassiopeia A, discovered by the telescope, provides valuable insights into the general contributions of supernova research and their potential impact on future studies. These findings are vivid examples showing that the universe is in a constant state of transformation and renewal. Finally, thank you for joining us on this incredible journey. Don't forget to subscribe to our Spacetime channel and hit the like button. We will continue to explore the mysteries of the universe in our upcoming videos. Goodbye, and see you on new discoveries in the depths of the universe.